Okay, so welcome everyone to this new episode of EagleFly The Experimental Debugger. Today we'll continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and be welcome. If you have any questions, please post them on Twitter, YouTube, or in the Hanmi Network site that, if you guys don't know, is this site over here. It's called Hanmi Network, and inside there I posted this post show my colleague, and where I basically explain the project, show the current output that we find, and information related to the project, and links to YouTube, Twitter, etc. In this place you can post any questions you may have, and I'll be there to answer. As I explained on the last video, this Hanmi Network is a site where you can find different projects. It's a community of developers where you can find different people making awesome projects, and if you would like to follow them as well, you can find something. Probably you can find something interesting in here. And yeah, so yeah, we have the Hanmi Network community, and yeah. So with that said, I would like to start by opening the project. So if you remember, we can see that the last thing we did, if I do remember, let me open the debugger, was that we disassembled another instruction that, if I remember, is jump instruction with an immediate 8 relative offset, which by itself, it's a really simple instruction. There's nothing more to it than I can show you there. Yeah. Oh my god. Here you go. There we go. We have a jump FFFF8. You know, it's an extended. It's a byte that is an extended to 64 bits. That gives us an address, an effective address. Of course, this is not an effective address as it is. You know, it's just that we are missing the addressing that we're looking. Since it's a relative offset, it's missing the the instruction pointer that we are assuming here. We have an instruction pointer that we are going to add this value, and when we add this value, that's the real address that's going to be copied to the EIP register. Okay, so that's basically the instruction, and we can make others as well. You know, it's pretty nice to go that route and do other jump instructions in the same way as we do it here. For example, we can do this. Well, this is not valid in 64-bit mode, so I'm gonna skip this one. we can do the 32-bit one, you know. It's a jump near as well, and is relative to the RIP, you know, equal RIP plus 32 bits displacement sign extended to 64 bits. So we can do that as well, just to see how it can be done, you know. So that one should be, well, yeah, let's do that. I was just thinking about what does it mean, the encodings for this RMR or something. Oh, R means that we are gonna have another M encoding, I believe. That was the thing. But it has a -4. That means that it's not exactly that. Well, we don't care right now. It's an extended opcode, isn't it? Yeah, this is an extended opcode. Okay, so if we do E9, let's do E9. How can we encode that one? It's basically the same, but the outside is a 32-bit. So that means that we need something bigger, you know? So if it's 32 bits, is that we are offsetting like 4 billion? 4 billion bytes? It's not a short offset anymore. And normally, well, actually, we just need it to be bigger than 127 bytes. You know? We need it to be bigger than 127 bytes. Which for the test assembly probably is not gonna work, because we don't have bigger than 127 bytes. And we need, if it's a relative, we need a label for that. So, for example, if I put it right here, I don't know how much work will be there. We can even put it positive so we can just test it. Of course, we can probably write more code and check it out, but let's see. We can open the file. That's alright. It's a 5A thing, so I know that this is it's a byte as well. It's not a 32-bit offset. So we need something bigger, and we need something at least the double as big. So we can probably just copy the code here. We don't care too much. Something like that. There you go. Now we have an E9, and we need a bigger offset. And now we have different blocks. You know, we have jump this E9, and then we have where is the other jump? Here's the other one. This one as well has a 32-bit thing. It's a little bit smaller, and we have another here. This is smaller. You know, it's a short jump. It's a B5A, and this one is an E906, and this one is an E9B6. Now this jump looks relatively bigger, you know, because, well, it's B6000000. That means that it's a 32-bit displacement, which by itself is, I mean, it doesn't occupy a 32-bit thing, you know. It doesn't need it to. But it's gonna jump to 41.128, which is here. It's gonna jump here, and yeah, it's just like this one. It's just as a 5A thing. And this one, so I don't know why it chooses it to be that way. I mean, if you just needing a byte for that. For example, the E, where is it? This is bigger. Okay, yeah, this is bigger. You know, it's an 0115. This, of course, needs bigger than a byte. So yeah. Yeah. Well, we can do this, I guess. It's not gonna be particularly crazy to do this. we have to close this stuff. And I would like to start by adding the thing. So yeah, well, on the initializing, we already have the jump instruction, so we can just add the thing. So we can just say we have push entry. And this is just the same. Mother precision, rectum, mother RAM, operand count, effective, immediate size. It's gonna be operating mode as well. The immediate size is gonna be 32-bit, and mnemonic name count just the same. Operation mode is it works in 64, yeah, and in 32, so we can just put both. And we have this thing, we don't care. And that's it. Compile. So this is not a short jump anymore, it's an inline, so we can look it on the one back just to make sure that we are looking at it correctly. So we have E9, we have this one, it's a near, it's forced to x64, and on 64, you know, and near JC, I don't know what JC means. Oh, okay. The instruction contains a relative offset to be added to the instruction pointer register. For example, jump OE9 loop. Okay. JC and C means that word for 16-bit operand size or double word for 32 or 64-bit operand size. Mm. 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 Okay. So this is an effective. This is an effective, isn't it? This is an effective. Okay, my bad. Let me move back here. Yeah, I forgot it, but yeah. Thank you, Mr. Isa. Where is it? Here we go. This is not an operating mode. This is an effective. Yeah. So the thighs is 32-bit, but we need to know that this is gonna be 64-bit mode, but the operand size is 64-bit mode. Now it says that it's forced to 64-bit mode. So that means that it's sign extended, So that means that it has to be sign extended to that quantity, But the value can be a word or it can. Now this is a little bit busted because, well, it's not, because if you remember in the instruction itself, it tells us that it was here on the nearest jobs. So it can be 8, 16, or 32 bit immediate value. This value is set to the value in the EIP register. Here, the EIP register contains the address of the instruction following the jump instruction. When using relative offset, the opcode for short versus near jumps and the operand size attribute for near relative jumps. determines so that means yeah, because we have 16, if you remember. Where is it? I mean, we have the 16 option is the one that we passed away because it's not encodable. So we have the 16 option here. It's not valid, but it's possible to have a relative 16. So we're gonna have a value that is 16 size, and that's gonna give us something about it, you know. It's not supporting 64-bit mode, so it's whatever. So, but this is telling us that it's an extend to 64 bits. So normally, yeah, I mean, I think this is more like the thing. Yeah, because remember we have two values, so the immediate value can be 16-bit, but whenever we are working, we have to think of the operating mode, you know, because the operating mode is gonna pretty much decide that. And now I don't know if this is forced to be 64-bit mode. I mean, it's forced 64-bit mode on. Look at this. It's well, I don't see it. Let me. There you go. So yeah, it's F64. You know, we are looking at this. That means that it's a near jump and JC, and the operand size is forced to 64-bit operand size when in 64-bit mode, and prefixes that change that is just invalid. Now this is only for 64-bit mode. I don't know what happens when it's not enforced, you know. So whenever we are not in 64-bit mode, we probably want to change it, you know. Yeah, because how to say, so the operand size means, because they use operand size in both things, you know. So in one tells me that, I mean, here they tell me that it's 32 bits for 32 or 64. That's true because we see it on the encoding, you know. We see it here. Here is 32 bits, you know. It's not bigger than 32 bits. It's 32 bits in 64-bit mode. So that means it's forced. But whenever we have the E9 with CW, that means that the encoding is 16, then it's gonna be 16, you know. It's not gonna be uploaded to 64-bit because that's not possible, you know. So that means that we have to do a check in there, of course, for 64-bit mode and stuff like that. But it's just that we can leave that later. It doesn't tell me anything here about if it is yeah, I mean, this is not, I mean, it's not the thing that I'm thinking about, you know. It's more like the thing we have. And in fact, we don't need to ask the question. We can just encode it for 32-bit mode and see what happens, you know, which is another thing to do. But for now, we're gonna keep it that way, you know. So where is it? Oh, okay, so this is the operand type. Yeah, okay, so I was misunderstanding the option there. So yeah, the thing is that we have the 32-bit one here, so that's it. So that's it. I don't know what's gonna happen. Probably it's gonna do nothing. It's gonna do nothing. It's gonna, yeah, we have E9, that's correct. So we initialize the instruction decoding. REX and mnemonic entry. What about the mnemonic? We have an entry. It's a jump. That's correct. It's a jump with operating mode, and it has an immediate size of a door. That's correct. So if we go and fetch here, we're gonna say, well, we don't have anything there, and go and fetch on the register, and then the register operand size is gonna be invalid, you know, and then fetch immediate operand, effective operand size, you know. Oh, okay, I was like, what? And we have that, and then we got that, and then this doesn't work right now for that, so it's gonna be busted. So yeah, I was just like looking at it if I can run it, but let's just solve it because we already know what's gonna be the thing that we need to do. Fetch immediate. So now let's go back to the one on fetch memory. Because the fetch memory has the complete one, well, not the complete, but then it has the 8 and 32 one. That means that we can do both, yeah. And we have to get the correct data from here, you know, because since it's on the least significant byte, we need the most significant one. So here we don't have a displacement by itself. Well, yeah, it's a displacement by itself, you know. So actually it's a displacement. Yes, it is. So we can call this displacement. Why would call it effective operand size? Because that's more like what we know. So the effective operand size is going to assign extend to 64-bit mode. But yeah, we need here the immediate operand size. My bad. Immediate, and then we have then, and then here immediate operand size, and then we go for the sign, and this is not the immediate anymore, this is on the byte. And then for int32 index, this is the same. We are just going to assign extend the data information based upon the data that we got from the sign. And the last thing, we just print the bytes on reverse order, and that's it. Yeah. That seemed to work. So let's do that as well. We have effective operand size of 8 and an effective immediate size of 4. And the byte 0, that means that the sign it's 0, and then from the effective to the immediate, we're just putting the sign. So if we see the buffer, there we go, and then from immediate operand size, we just do the same stuff here. Context I by count plus equal immediate operand size, and now we put instruction that's correct to jump 00015, and now C by is pointing to EB, which is the other instruction. And there you go. Now we have a jump FF8 000115, push or top, push REX, move SPL, REX, RBX.14, REX times 2, RBX RBP REX times 2, RBX RBP REX times 1, FFFF REX times 4, 0032221100, move RBP RSP plus R12 times 8, 0032221100, move rate R12, move rate R13, 0000, move rate RAX 000332221. Yeah, everything looks fine. Okay. So that's nice. Now we print another instruction in there, and now what I would like to do is to say is that if you see here, we have the same code right here, you know? And since we have the same code, we can just compress it, you know, compression-oriented programming, as we do it all the time. So, or we try to do it all the time. Yeah. So we can just say that we are going to copy this, and we're going to do our own. Right here. So for this case, this is gonna be left off outside. And here I can call it So this is the encoded size, and there we go. This is gonna be encoded disp, encoded disp, and this is gonna be immediate operand size. Immediate operand size. Sorry. This is encode size. Encode size. And this is byte sign. And then effective size. And then this is encoded size, and this is a buffer size, out buffer count, sign buffer, there we go. And then here we have encoded size. Here we have code displacement, and this is just the same. Yeah, that's it. Goodbye. So if we do that, we will need just to call this thing on each one of these, so that we just say, hey, we're gonna have that, and we're gonna pass the disassembling state, and then we're gonna pass the encoded disp, which is disp, and then the encoded size is gonna be the displacement, and then the effective size is going to be effective address size, and then the buffer is the same, out buffer count, buffer size, and in the same way, this thing right here can just be that thing, and here we're going to have the immediate, the encoded size is going to be the immediate operand size. The effective size is the effective operand size. The car buffer is just the buffer. The out buffer can is just the out buffer can. The buffer size is just the buffer size. So yeah. Oh, in fact, well, this is more like this, I guess. And let's see what happens. Let's see. Let's match it against our encoding. So we have, and let's copy these ones because we haven't copied them. So we have our jump, that's the same, O15, FFF8, and push R12, push REX. Now OX F8. Oh yeah, it's F8. Okay. So we have FFF8, push R12, push REX, move SPL REX, move RBX R14 plus REX times 2 plus 0, 0, 0, move RBX RBP plus REX times 2 plus 0, 0, 0, move RBX RBP REX times 1 plus FFF, move RBX REX times 4 plus 0, 0, 2, 2, 2, 2, 1, and move RBP RSP plus R12 times 8 0, 0, 2, 2, 2, 2, 2, 1, 1, 0, 0, R8 R12 R14 0, 0, 0, move R8 RAX 0, 0, 2, 2, 2, 2, 1, 1, 0, 0, move RAD RAX 0, 0, 2, 2, 2, okay, okay. REX RDX, add by pointer REX FFS0 or B, FAT ST0 ST1, ST1 ST0 FUCOM, FLD 0, 0, 0, 0, 0, 4, then resume, PLine R, XM0, XM1, 08, shift left double, AX03 at AX store pointer 000. So there you go. We have the same disassembly, and we have already already compressed the information with the push displacement thing. So that means that we can just erase this stuff from the face of Earth. And now everything got simplified. We have compression down there, and probably in the future we can, now memory operand is already compressed as well, so that's kind of nice. And there you go. So run it once again. And there you go. So now that we have that, we made that simple compression, so we can continue. So what else can we do? Let's try another instruction. We can do another jump there. They seem like a really good thing to do. Shall we try an x86, or we continue with 64? I think it's better if we continue with 64, because the x86 thing, once we have the 64 more detail, it's gonna be better. One, because we already have all the setup working correctly. I mean, we have the assembler in 64-bit mode and etc, etc. So we can just play around with this stuff, and once we got the assembler good, the disassembler, the x64-bit mode correct, then passing up to the 32-bit is gonna be relatively simple, let's say, because it's just, 64 is an extension of x86, so that means that it's pretty much it's like having the extension plus x86 by itself. It's just like having some constraints around. So once we got everything, it's easier just to put some constraints to the thing instead of building. Probably it's the same, but just saying that we just should continue with 64-bit mode. So if we are going for that route, we should do, these are not encodable on 64-bit mode. It's not S, it's not no, I don't know what it means, but it's not valid. Probably this is not encodable. Not S is, I don't remember. but I mean it's sufficient to say that it's not. But probably it's good to find. It should be good to find the thing here, isn't it? So let me try to find it out. Okay, now prefixes. Now prefixes. Okay. Okay, not supported. Okay, not supported. In the case of instruction syntax that requires an address override prefix in 64-bit mode, and it's not supported. It's an address override in 64-bit mode resulting in a more specific execution behavior. So that means that it's not supported, you know. But oh, okay, yeah. So yeah, of course it's an address override because the only way to get, well, you can, isn't it? Well, yes, you could because it's an operand. You could because you're modifying the operand. So it's just like saying, oh, we're gonna have an address override, and it's not supported. So if you wanted to do that kind of stuff, you need to have a 66 or 67, sorry. No, 66 address operand size override. And in that case, well, it's not supported, you know. That means that if we do that, whatever is going to happen is that the processor is going to treat it as special. Probably it's going to work, probably not. Probably it's just going to do bananas. Who knows? Is one of the things that they are not. They are like kind of the loopholes or the holes in the processor. Like you can touch a lot of stuff. You can make a lot of stuff with the processor that is not supposed to do, and that's kind of a problem. Yeah. That's something interesting, and there's many ways to check and test that, like fuzzers and stuff like that. That they pretty much beat fuzzing with instructions and test all the unsupported instructions that they can find and see their results. And I means a new instruction in 64-bit mode. MP, in the case that RX prefix does not affect the legacy instruction in 64-bit mode. And not encodable. Okay, good. So that means that if we want to do the FF4, we can do it. It's gonna be an extended opcode, you know. So, and it's a jump near as well, you know. It's an absolute now. It's not relative, so that's nice. And it's indirect. That means that we are using RIP equal to 64-bit offset from register or memory. Okay. So that means that we can do it. Probably we can do it. Where right now we already test this, so we can just compress it back to the thing. Probably. My bad. it has to be a 64-bit one, you know. If we try to do the 16 or 32, it's just not gonna do it. So let's try FF. Why not? Um, uh, uh, so what I can think about is using an REX, a 64-bit register, you know. So that means that we can do, where is the push, is the jump. No, you um, something like that, I guess. Let's see. So what happens if we do that? So we have the XOR RAX, and then we have FF is 0. We have to jump to RAX. Okay, yeah, that's encodable, and it's 0 because it's using the mother M. And if we see it on the no, this is not a far absolute indirect. It's a near absolute indirect. So let's read about that here just before going into the thing. So that means that here we have is 0. So let's see the FF here. It's under 1 byte. And we have a group 4 on the FF. We are on the last one here. Index group 5 1A. So it's group 5, so let's go to group 5. I'm gonna duplicate this. And I'm going to copy this into here. So we are on group 5. Here you go. This is group 5. And we have memory on the mod, because we have 1B. The mod has to be 1 and the bits of 543 modern byte have to be the extension. So we're gonna have 0, 0, 0, 0, 0, 1, 0, blah, 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 all the combinations. So for FF, we have is 0, that means that we have 0, 0, 0, 0, and then we have E, that means that E is 1, 1, 1, 1, 0, and that means that we have 1, 0, 0 on the rec and 0, 0, 0 on the arm. So we have 1, 0, 0 on the rec. So we have a near jump with force to 64. It has the F64 and the EV. Near jump EV. We can have a far jump MP or a push D64 EV, a far call EP. So it's a little bit sparse. Most of them have to be with control instructions, but yeah, I don't know exactly why the reason they are encoded this way. That's a nice question to answer. We have OF00, we don't care about them. So yeah, we have near jump force to 64 and 64 be moved, and we have EV. EV means if we go for E, we have a modern byte follows the opcode and specifies the operand. The operand is either a general purpose register or a memory address. If it's a memory address, the address is computed from a segment register and any of the following values: a base register, an index register, a scaling factor, a displacement. Okay, and V on the other side, we have the word double will require word 64 remote depending on the operand size attribute. Okay, that's true. That's totally true. So probably one thing I should mention here. Well, I'm gonna do the instruction decoding. I mean, we're gonna decode that instruction, and we're gonna see something that probably I am like missing out with the flex, you know, with the operand things there. That's probably wrong, but we're gonna find out. You know, we have to find out that we are wrong. So let's go and do that. So before doing that, I would like to encode the instruction itself, this one, as memory operand. You know, load. I don't know. Let's do that. Now, well, let's see the thing here, because that's the only way to do it. This is 1 byte. This is the thing. Where is the memory operand thing here? So we want to jump to an address, specify by that. So probably it's not that, but I don't know, some displacement. And we need this. So what about that? What about that? that thing. And what's going on here? Well, probably it's a little bit busted. So we have a jump, move R8, RX displacement to 2. So what I can say about this, we have an FF, and then we have a mother RAM, and then well, this is the displacement 32, isn't it? Because 25, you remember, well, 25 on the grip side, let's see, 25 on the grip side, we're gonna have 0, 0, 1, 0, 0, 1, 0, 1. So we have 1, 0, 0 on the same math, and then we have 1, 0, 1 on the RM, but we have 0, 0. That means that we have on the rec field. Yeah, that's controlled by the rec, and the 1, 0, 0, it's controlled by that. So it's the same one, you know. This is the encoding, yeah, the opcode extension that gives us the right thing, and we can say that we have 1, 0, 1, so that's on the mother RAM. Yeah, if you remember, the first one here is 1, 1, 0, 0, 0. That means that we have REX on bit field here. We have a register operand because we have 1, 1. And this is like, oh, it can be memory or 1, 1. You know, memory or 1, 1. This is forced to be memory, but this can be memory or 1, 1. Memory or 1, 1. So that means that here, on the first case, we have EIX, and because of 64-bit mode, you know, effective address size has to be 64-bit size, you know. So that's it, you know. The only thing that changes is that it's forced to be, you know. That's important to see. So what else? And yeah, because we don't have an REX prefix that tells us that, because we don't need an operand of that size. We need an address of that size. So the address can be gotten from 64-bit mode in that way, you know. But the thing is that we have to keep it that way, because if we add a 66 operand size over prefix, or sorry, a 67 address size override prefix, it's not gonna change at all, you know. It's invalid in the first case, in the first place, sorry. And yeah, and the REX prefix pretty much doesn't change anything at all, or yeah, it doesn't, because it doesn't need it. or could I? Could I do it? Let me see. And the second, it's because we have on the rect field we have 100. That means we are on that column, on this column, and then we have 101. So we have, and we have 00 that here and here. So that means we have a displacement 32 and the rect field is occupied, you know. That's something that we cannot change. But we have 101, displacement 32. Okay, so let's see if we can do all the addressing modes in that case, you know, just to check, to be sure that we are doing something logical here, you know. So first of all, I'd like to see if we can have REXs, you know. Well, this is gonna show me if we have SIBs. Now we can just have ESP. Oh, we can. So we can have that. Okay. Let's see that. So this is the displacement, normal stuff. Here we have 41, yeah, we have an REX prefix, so the combination can be done. We have FF, and then we have 65. Here we have a 65. This is the mod RAM, and this is the SIB, which it needs to be added, so that's correct. And this needs an operand size override, which is possible, you know. Look at this. We are looking at the operand size, address size override there, so we have to use ESP for that. And then we pretty much have FF on the thing. Where is it? How to say? have 67 FFs, 24, 24, 67, which means, yeah, advertising. We have FF, which is the case, yeah. We have 24, which is the mod-ram by, and then we have 24, which is the SIP by, because for ESP we need SIP, if you remember. So if we go for ESP, you know, we're gonna have 24 on the mod-ram. That means we have 0 0, we have 1 0, and then we have 0 1 0 0. So that means that we have 1 0 1 1. We have this thing. And the RM is 1 0 0. That means they need this thing here, SIP. And then on the SIP by we have 24. That means that we need to have the same thing here. It's gonna be 0 0 1 0 0 1 0 0, and we're gonna have 0 scale. And then we have the index, then we have the base. So the index is the same. Index is 1 0 0. That means that we have nothing on the index, but we have it on the base. We have a base, and the base is ESP here, 1 0 0. Yeah, so that's correct. So my question is, so then what is not possible should be this, isn't it? Exactly. The operand size is just invalid for this. It's forced to be 64-bit mode, you know, because that's the way the instruction works. So yeah, so that's the thing, you know. So we have effective working here. So we misunderstood like the forcing of stuff. It's just another flag that we have to put there so that it works, you know. So let's make that transformation, and let's just add the whole stream of these things. This shows that jump is forced to a 64-bit mode operand. We can have advertise overrides. But no operand size overrides. That's important. Okay. So that's what the flag does, you know. That's that's the functionality that we have to do, you know. So let's start by JumpInstruction. Probably that's good. That's a good starter. And then we can do the other ones. So let me see, let me just write so I didn't skew it up. So yeah, so let's add an instruction. So let's add it here. Boom. What? No, it's not here. Like what? This doesn't go here, but this does. Okay. There we go. Now this doesn't go there. Now think about it. Good to remember because it's an extended opcode. So what we need is the, where is it? Oh, I put it on the wrong place. There you go. Now is this correct? 62? I don't know. Probably yeah. Did you find it somewhere? Oh. Okay. These are invalid on x86. Okay. Okay. So what we want to copy is the modram by. That's the one that we are looking for. And abstention IDs, escape the byte IDs, escape the 8 byte IDs. Okay. Now these abstention IDs should be the modram bytes as well, isn't it? At least should. I don't know. This is the modram byte. Probably these are too, but well, whatever. So we are gonna have an E0, that thing. We're gonna have another one on the extension one. There you go. And let's go to the extension one. There you go. So let me copy this. Let me go for the jump. I'm gonna copy this. I'm gonna put it here. And this I'm gonna call it jump. And no. Jump entry 02. There you go. 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 Doo-doo. Yes, we do have a modern by. What can we say about this? Well, we just have one register, so what can we say about it? Probably we don't care too much about it. It's false. Let's say it's false. We just have one operand because we have an extension there. And how do you write that thing? Well, we don't write it because you don't have anything, we don't have displacement in this case. So it's not that we have an, this is invalid. Oh my god. There you go. We have an invalid thing there, and here it's also invalid. And we need tables. Mnemonic entry. I want to copy this stuff all the time. All the time. So let's fill it ourselves, you know, because there's not somebody who, I don't know what's this one, but I can replace. Probably, I mean, actually this is, oh my god, this one is like that. Okay. Okay. So we don't care about this, we don't care about this, probably we don't care about that. And okay, let's do this. Let's do this. We don't need this. We don't need this. We don't need this. We don't need this. We need we need this probably, and we need this, and we need that. We don't need this, and that's all we need. Okay, so we need that. This is gonna be this. Then the memory operand size, it's gonna be that, and this is gonna be I wanna say this. this is gonna be that. That means that, for example, if we had here on the test system, now here we're referencing that kind of thing, but if we have here EAX, for example, that couldn't be possible. It's telling me that the instruction does not allow near indirect addressing. Yeah, near indirect addressing, which in this case, I mean, it's kind of stupid because this is also indirect addressing, and it's also near. So yeah, I mean, it's not correct. I mean, it's incorrect, but it's not incorrect by what it means. So it's just not encodable, okay? So that size is 464. That's important, and it's gonna be effective, you know. And yeah, and this is the operand count. It's gonna be 1. And the mnemonic name is gonna be, I'm gonna say it's gonna be, well, it's the same, isn't it? It's the same as the jump entries, this stuff. I don't know if we want to make function calls to initialize this stuff by stutters, because this is starting to get things. Like we can make even macros or whatever. Yeah, we can think. For now, I'm gonna leave it at that. But let me put it to. So we need data size 464. Data. 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 Data size. Data size. So I think, yeah, this is gonna be forced to 64, and in the same way, these two things over here, they have to be, and this is the entry 1, for 64. Which mm, I mean, all of them are forced to 64 when 64-bit mode, but this cannot be 8-bit, you know? It has to be sun extended all the time. So we can say that 464 is like effective, but whenever it's in 64-bit mode, it's just forced to be that case, you know? We can say that, you know, just by assumption. So yeah, I guess. And in that case, we don't need to have a combination of them, which is not bad, because they are telling me different stuff, you know. Effective is telling me, oh yeah, it's effective whenever we are not in 64-bit mode or forced to 64. In that case, the 464 semantic thing will only care about if we are on 64-bit mode, we force to 64-bit mode thing, you know. If we have effective, then we can just play around with that, you know, and this can be a forcing of it. So yeah, we want that. So it's simpler for us to say, hey, this is effective, and this thing, this. But if that's the case, data size 464, data size effective, that's okay. And this is okay, that's the way it goes. Effective in mid size. That's correct. So let's jump to the other jump. And here we have the effective on both, you know, and 464. So yeah, that's the thing. So if we do it that way, I wanna go to tables themselves and define we have two of them that defines it like that. But we haven't used it, so, and we cannot have this as a big flag, so probably we don't want to have that as it is. So I don't know you guys, but I feel like we want to have this as a thing. And it's gonna be called so I don't know why we have all this stuff. We have this, but we don't use it. well, we don't care too much about that. So we want to have well, we don't need to have all of them, because if you think about it, well, I haven't seen anything that it doesn't get respected on both sides of the operand, you know. Well, for example, it can be this, that is the by thing, and it has to be sign extended or force, and then this is AL, which is different. So yeah, they can be operand, relative operand. For example, AL I don't know if it means AL. So we have an L. I'm sorry, AL. Oh no. I was like, what is AL? It's like, oh, it's the register. This is selecting the AL register to the immediate thing. So that's it. That's why it's the same size, you know. So we have the same size, and here, well, here we don't have the same size. It can be, depending on the size attribute, it's gonna be sign extended. So but it's still the operand size attribute and stuff like that, you know. Yeah, and we're gonna have stuff like that. So I believe that we can have this, you know, operand of flex, and then this thing, yeah, I mean, they can be Uint32, I guess, or they can be EagleFly operand data type, data size. So we had it before. That's gonna be like that. The operand count, mnemonic name, the flex. There you go. And then if we do it that way, we have to change the whole stuff, you know. There you go. We have to say that we are gonna have an add entry register of flex, and this is gonna be the thing has this, and the register operand size. we don't need this anymore. Let me think about that. Sometimes we do, but I don't know. We can just do that. Operand count, because this works for every one of the operands. So if it's an immediate, the A has to be an extended, but we can just tell it by. I mean, it's just the immediate one that cares about that. I believe, I don't know, I don't remember, but let's go one by one and see that. Let's compile. And for example, this is telling me that, yeah, we have a word there. For example, bound entry. The bound entry, I don't remember what was working, but what we were working with that thing. The other entry is just invalid, immediate size, data size byte. It has a byte thing there, and I don't know if it's forced for this one, for example. We have to check it out. We have it on the H, the N. Did we erase it? Probably it was, yeah, it's not 64-bit mode, so yeah, so we cannot test it right now, but it was it's valid 64, 32-bit. Oh no, we don't have it here. No, we have it here. Yeah, it's only 32-bit, so yeah, that's too sad. But what about the bound? The bound, yeah, the bound it's also only valid on 32-bit. And it has dwarfed operand sizes. It doesn't have an immediate, so it's invalid. So yeah, it cannot be, I mean, the way we are doing it right now, because it doesn't, I mean, we need to specify that invalidates the immediate, you know, so we cannot just get rid about the immediate. Probably, but about the memory we can, but we can, it's better if you just specify everything, you know, for now. You know, probably in the future it's going to be more complex, but for now we are thinking that that's the case. For example, the move 0 0, that this is possible. We have true, we have a register, it's effective. We don't have a memory thing there, and it is because we never use the memory operand size at all. We just care about the register operand size, right? Because that's where we say, hey, we're gonna go and fetch it, and we're gonna go and fetch a register, so please tell me that you were right. And we say, hey, we have effective. If it's effective, we just put it effective. If we have a for, we can just add here a clause that it has to be forced to 64 or forced to something, you know. So let's see the usage code here. So yeah, we use it that, and when, yeah, this is the most important cases, you know. This is the most important case because it's the place where we override the effectiveness of the stuff, you know. On the other side, we just use it inline, so we can just call it without effectiveness and say we have an effective operand size of blah, and we get it. So that the operand, the factory register operand doesn't care about the register operand size, you know. That's the reason why this is the first entrance for that, the second, the third. This is, where am I? This is another call, get a mnemonic entry, okay. So I'm getting mnemonic entry, we also use it because we have a register possible thing. And we define it as an operating mode because the operating mode, I don't know why, but it was defined by the operating mode, not by the data size, you know. So that was why we have that thing. And register operand, register. And yeah, so if we go and look to memory operand size in the other case, you know, let's see where we got it. We have that, and that, but we initialize it, but we never use it, you know. And the reason is because we need to have a register operand size, you know. So the register operand size is the one that gets defined across the places. So even though we were using this stuff, we can just simplify all this, you know, and say that we don't have a memory operand size. Where is it? We can just say, hey, we just have an immediate size and register operand size, you know. That's all we got. That's all we got. And yeah, we can have different flags in that case. We can just say, well, we can have flags inside of it. It's not gonna be, well, we can keep it in there, you know. It's not like too crazy. So in here we just have that operating mode, register operand size, immediate size. We have the effective one, and then I'm gonna move this, I'm gonna keep that, something like that, and then over here where we have this thing, Okay. And I don't know if we want this warning. Well, why not? Mm, so now we have that, and we can just say, hey, we're gonna have that. We just care about the register operand size and the immediate size. So the the same thing we had before, but or the thing that we were looking for, like just having two things there, three in this case. But yeah. So that means that if we go to I'm gonna go to fetch immediate. You know, we have this thing that it was operating mode thing. Now it's not gonna be operating mode. We have to see, so now we're gonna flag it, you know. let's gonna say the switch case effective operand size data size effective, I want to say address, data size 464, case blah blah blah, data size effective, and then we gonna do this where we're gonna say, well, you know, this is gonna be not operating mode, but this is force. So that means that if we are on 64 bits, data size 64 bit. If not, it's gonna be data size effective, and then now I don't know if this is kept on the switch statement. This is gonna be just be in place because we're not breaking, and we can say well, it's better than an if statement, I guess. That's the case. So we can just say if effective operand size, data size force 64, if effective operand size, data size effective, data operand size equal to this state, and this is where we say that I have the effective thing on the operand here, and I say entry register operand size this is not well the effective operand size. Do we pass the effective operand size here? Since we're in 64-bit mode, we are always gonna get data size 64-bit. But on the other cases, the thing is gonna be like we're gonna get past a value. So we probably want to pass the effective operand size as well here. So we can pass it, we don't care, it's good. Effective operand size, and this can be called effective. This is going to be called effective in size. And there we go. And then well, it's just this. But this, we don't have other choice but to use the effective one, I believe. I have no idea. I'm just making it up. Well, we can just comment for now, since we don't have any kind of usage case here. Well, we're gonna do it just in a second, but yeah, for now I'm gonna keep it that way. So we're just gonna say that, whatever, and we can just assert that effective mean size is different to effective data size effective, for now, and later we resolve that place. So in here we just need to effective operand size as well, and probably both, I guess. Effective, there you go. Yeah, in fact we care about the well, it depends, the other size and the operand size, but yeah. Fetch immediate operand. Now it depends. We care more about the address size, because it's the address size that we care about. At least for now, because these are address. But yeah, I'm just gonna leave it that way. And the thing we had before, I don't know if we have other ones that gets forced in that way. For now, I don't see it. Let me put it either fetch immediate. Expand this and use effective size. Yep, there you go. So on the fetch register thing, right here. What we were doing here is that we have data size effective, so we can keep that way, you know, just that way. Yeah, we don't need to change anything, I guess. And the forced, for this case, on the data tables, we don't need to, no, on the initialization, whenever we have this kind of thing, we don't need that. Is that all? Oh no, data size forced. So there you go. So I want to see what happens. Did we add it? Yeah, we added the next with REX. Oh, and if we want to do it, well, that's something we forgot. But yeah, we are gonna need to change this, you know, to be a little bit more if entry register operand size. Now we have it on the register operand size. Is that the case? Where is it? Force. Yeah, we have it here. So we have it. We have the same here. Data size 464. Then we checked for the thing before. Now I don't know if we want to modify the register operand. Probably we don't want to do that. Yeah, so I'm gonna say unit32 operand size equal to entry register operand size. And then even though it's a copy, yeah, we want to be safe there. Register operand size, and this is operand size, and this is going to be effective, and then operand size, effective operand size, entry register operand size. Yeah. Yeah, that's it, you know, that's all we have to do. We don't need to have the flag system, whatever. We just need to work here. Need to see what we need to do here. Yeah. My bad. Okay, so I think that's all. We have to check it out. So the C byte is gonna tell us that we have FF. That's correct. We get the entry. We have a jump instruction. We have rect model RAM. We have a model RAM. We don't have an effective. We have a register operand size of blah. But now we cannot see what it is. But yeah, whatever. Operand can. Well, we can see it. You know, it's 2000, which is, yeah, it's 1 minus that. So yeah. There we go. We're gonna fetch a memory operand, which in this case we say, hey, we have a memory operand. You have a modern prison. That's what I would say. And if it's register operand, we go and fetch it, and we say that operand size, and operand size it's forced to that. Then we just say, well, what we're doing here now, operand size is gonna be that, and that's not okay, probably that's not what we want to do. That's what we want to do. So now have an 8, we have fetched the register, and we're gonna fetch the error field. That's true. The error field is the one that has the register. That's correct. the buffer has RAX, that's correct. And we have a byte count of 1. Now the context up count is 1, so if we go and fetch the register, and the operand size is just going to be the same because it's on the stack. It's going to not do it because we already did it, so we don't go twice in this. And context up count, and then fetch immediate operand, and we're gonna go try it. We don't have it, so we just move it. So we print instruction, jump to RAX, that's correct. And C byte is pointing towards E9, which I know if that's correct. Yeah, that's correct. So let's see the next transformation for these little ones. We're gonna have that, and then we have 64, and we are just gonna sort that, and then we just say, well, you know, we have 64-bit mode, so we just push the displacement to that. So the buffer is 015. Print instruction, that's correct. C byte is CB now. There we go. So let's make the match one more time. This is jump rex, jump blah blah blah, jump blah blah blah, push R12, push RAX, move SPL RAX, move RBX, R13 RAX times 2 0 0, move RBX RBP RAX times 2, move RBX RBP RAX times 1, move RBX RAX times 4, move RBP R12 times 8, R8 R12, R8 R13, R8 RAX, RAD RAX, move RAX RDX, add RDX FF0 OB, FF ST0 ST1, FUCOM ST1 ST0, FLDO4, BM resume, Beeline 018, EAX03, EAX stuff, blah 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 blah. So yeah, that's good. That's really very good. And yeah, so I think that's good. That's really nice. Now the only thing I want to do now, just for finishing this up, I just want to say that over here I mean I don't want to like continue printing the nulls there, and we can do it really easily. In this case, we're gonna print one time that thing. We don't care too much, but you know, probably want to do this different. There you go. And in fact, well, that's good because we know that we didn't find the entry or something. or you can probably make a login there. Probably it's better. We're gonna do that on the next stream. So yeah, yeah, yeah. Well, probably that's better. Yeah. So please, if you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Please make your questions relative to the thing we did today. And yeah, so I can answer them. Yeah, I think that will be all for today. I would say thank you very, very, very much for coming, and I will see you on the next stream, full of code to make and surprises. Yeah, take care.